instead of describing it formally on a paper, we will describe it formally in a proof assistant. So, okay, no, yes, this one. Okay, so this is the outline of the talk. So I will shortly introduce the subject, and then we will focus on a paper by Bodini and Taro, which was presented in 2017, and that we formalized using the code proof assistant. And then we'll see that there are many data structures that we need to manipulate to do this formalization, and we present a general framework in Coq where we can prove the isomorphism between the various representation, and then we will conclude. So a bit of context. So what took place in CLA before are two talks by Giorgetti, Dubois, and Zeilberger. First one was in CLA 2015, and it was about the projection between closed lambda term and labeled almost trivalent maps of type 1. So all the objects were formalized in Coq and Prolog, and no formal proofs were carried out, only some validation by enumeration using the Prolog system. So here the idea is to do stuff where we do actual formalization and actual formal proofs on some slightly different subject. And a second talk was given by Alain Giorgetti and Catherine Dubois in 2018 about the introduction of blooms in the middle between lambda terms and maps, and some semantics for blooms and maps. And then again, Prolog specification and some random and Bound exhaustive testing. So the idea here is to shift from validation by enumeration and Bound exhaustive testing and this kind of stuff, so more formal in the sense of using the code proof assistant to prove some properties of the object we consider. So first of all, we consider a pure lambda term in the shape of De Bruijn. So this is basically defined by this grammar here. So we have either integers or lambda followed by a term, or two terms which correspond to the application. So when we implement it in Coq, it boils down to an inductive definition, and it corresponds to what we call unary binary trees, and they are called labeled Moskine trees, so LMT for short. And here is a definition in Coq of how we define labeled Moskine trees. And here we have a small example of a very simple lambda term and how it can be represented using this inductive definition. So here we have a lambda. So the lambda term is lambda, and we have an application of lambda 1 to 0. So 1 means that this variable is bound to the uppermost lambda, and 0 is the same here. And so this can be described saying, okay, it starts with a lambda, and then it has an application. And on the left side of the application, we have a lambda with a variable, which is number 1, which says that it's bound to the first lambda of topmost one. And then on the other side, we have just bar 0. Now we consider closed lambda terms. So the issue with closed lambda terms, so lambda term is closed if the label at each leaf, meaning its De Bruijn index, is strictly smaller than the number of lambdas above it. The problem is to talk with combinatorist vocabulary. It's not a catamorphism for label Moskine tree, which means that you can't define to be closed recursively directly on Moskine tree. You need to have a notion that some terms are open, and you have to know to what extent they are open. So if you just need one lambda to close it, or if you need more ones to close it. So once the solution is just to ignore the labels and just consider that you don't have zeros and ones, but you have just something which is a constant, and then you can define a closable property as well. So that's what is carried out in the paper by Bodini and Taro in Lobster 2017. So that's what we will focus on in this talk. So in the paper by Bodini and Tarot, they do some definition and proposition and a lot of implementation in Prolog, and small parts are carried out in a functional programming language, Haskell, and they define some enumerators. In our contribution, we say, okay, let's see how we can formalize that in the code proof assistant. So we have code definition, which are directly inspired by the Prolog one, or even by the Haskell code. The aim is to prove the proposition in code. We consider as well random generator as is presented in the initial article, because that's a good way to do some testing before proving. So we use some tools available in code, namely QuickCheck, to check to test some properties before trying to prove them, because as you know, it's very easy to make a small mistake in the statement, and then you spend several hours trying to do your proof, whereas it's a false statement. So the testing feature was very important to have the right lemma to prove, and then prove it easily. Okay, so to do that, we consider Motzkin trees without lambdas, without labels, sorry. So what is a Motzkin tree? So it's exactly the same thing as the LMT, except that you just don't have any natural number here in the first constructor. So it corresponds to a rooted ordered tree, which is built from a binary node, which corresponds to A, binary node, which corresponds to L, and some leaves, but you do not distinguish between all the leaves. And now we want to show what closable Motzkin trees are. So in Bodini and Tarot, you have this definition. A Motzkin tree is a skeleton of closed lambda terms if and only if it exists at least one lambda binder on each path from the leaf to the root. So what's written in red is what we consider as the definition of closable Motzkin trees. And then we will formalize what the skeleton is and what a closed lambda term is, so that we can show the equivalence. So here you have two examples of one closable and one non-closable Motzkin tree. So in the closable one, you start with A, and what's important is that at some point before reaching V, you need to reach L. So this is what happened here. You have A, but on both sides you have a L, whatever, I don't know how to pronounce it in English. And once you face a L, it doesn't matter anymore what you see below, because this L, it can always be used to close the term. And on the other side here, sorry for the camera, here you have an A, then you have an L, and it's easy to see that this side is closed, but this one is not, because you don't have any instances of L on all the paths here. Okay, so this can be easily defined as a recursive function in code. So you just go through the Motzkin data structure, and you just have a case analysis on the three possible cases. So the empty node, the unary node, and the binary node. And as soon as you face a L, you're closable. It doesn't matter what's below. And if you face an application, then you have to make sure both sides are closable. To do that, we face several representations. So the easiest representation is to have Motzkin trees, and we put them together in a record data structure with a predicate, which is called isClosable, which is the one we just saw. And we can put that together and do some reasoning about that. But there are other ways to describe a closable lambda terms, and one easy way is just to use this construction with only two constructors, LA and app. So LA say, okay, if I take from a Motzkin tree, I can create a closable. I just need to put a lambda in front. And on the other side, if I have two already closable lambda terms, then if I do the application of two of them, they're still closable. So we designed some functions, so closable to rect closable, which is going this way, and rect closable to closable, which goes the other way, and we prove the round trip lemmas, which means that if we apply one function and then we apply the other one, it's the same as doing the using the identity function. Okay, so here is an example. So you have a Motzkin tree here, and you need a proof that it's a closable Motzkin tree. So here you can check it's actually closable because of the two L's here below the A. And so this is the representation with the Motzkin tree and the proof that it's closable. And on the other side, you have the representation using the over construct. So you have app, which says you have an application, and you have two lambdas, and then below that you have whichever Motzkin trees you want, because it doesn't matter anymore if you have any lambdas or not, because you have already one on top, which enables the lambda to be closable. To carry out this work, we use the quick check, which is a cockpit of Haskell quick check, which is a way to test a code conjecture before proving it. So there are some technical issues to be careful of, but it's very simple. So we need executable properties. So it means that properties that compute Boolean values, not just statements in the way Coq usually deals with them. And we need random generators, of course. So some of them, they can be generated automatically, and some of them, you need to write them by yourself. So this generator, with the help of the combinators of QuickCheck, they can be verified random generators, so with some established properties. So we managed to generate 4 random generators. So the first one is just you generate, you have a generator for Motzkin trees. So it's fairly easy, it's derived from the Motzkin definition. Then you can have something a bit more precise, which is closable Motzkin trees. And this can be achieved by using the Motzkin tree generator and then checking for each Motzkin tree we build, whether it's closed or not, it's closable or not. And so you can just filter. So it's very time consuming because there are many more Motzkin trees than there are closable Motzkin trees. You can also write a specific generator which works directly with the rect closable definition, which means you build a Motzkin tree and the is closable property at the same time. So you don't have this filtering step where you generate a random Motzkin tree. You generate a random Motzkin tree which is closable, and then you can iterate to prove more, to create more elements. And then you can use the inductive definition of closable, and it can be derived automatically by the system from the definition of closable to have the random generator for closable. And so then you can test some properties. So here you have a test which checks whether rect closable to closable applied to rect closable of C is actually equal to C. And so you have like here 10,000 tests which are carried out. And so once you manage to do that, you're pretty confident you can try and make a formal proof of the statement, because it's easier to prove a true statement. Okay, you can do the same with uniquely closable Motzkin trees. So a skeleton is said to be uniquely closable if only if exactly one lambda divider is available above each of its leaf node. So which means you have to be a bit more careful, because once you have a lambda, you can put more lambdas. So you have this same approach with a record definition with a Motzkin tree and a property which verifies whether this Motzkin tree is uniquely closable. And you have 2 other constructors, which as those described in the paper by Bodini and Taro, which are CA and UCS. So CA is closed above, and it says you have either V or B. So it means that everything that's below the L, which you're looking for. And then for UCS, you have either L, and you take a closable, and you obtain a uniquely closable, or you have 2 uniquely closable terms, and you put them together as an application. We generate random generators as well for rect UCS, CA, and UCS automatically from the system. Let's go back to the characterization of closable Motzkin trees. So this is the definition I showed before. So Motzkin tree is a skeleton of closed lambda term if and only if it exists at least one lambda binder on each path from the leaf to the root. So to prove this equivalence, we have that as a definition, and we need to explain what the skeleton of a closed lambda term is. So first issue is how to formalize closed lambda terms. So as I said before, closed lambda term, they cannot be defined recursively. You need to use a notion which is the notion of open term, which is M open term. So there's a bit of literature on that. So the term M open comes from a paper by Bonini and al, which introduces this term in 2019, and it was used before with another name by Pierre Lescan in 2013. So lambda terms containing at most n distinct free variables, which is exactly the same as. So M is indicates the number of lambda we're missing just to have something that's closable. So this can also be formalized using COP. So you can define is open. So it's the same, but instead of saying true or false, you check where you stand before you compare with the depth, with the actual M, to check whether your level of openness. And then you have a record when you have your label Motzkin tree and you have your property M is open. And you can define it directly with an inductive data type using the code proof assistant. And so you can prove that these two representations are equivalent. So you have a transformation function here, and you can prove the two round-trip lemmas, which says that they are bijection, they are inverses bijection. Now we need a skeleton function, which is a label erasure function. So you take a label Motzkin tree and you just transform it into a Motzkin tree. So it's fairly easy to achieve. You do it by induction on the structure of the label Motzkin trees. So you just forget about the number, the natural number, which is the index of the variables, and you just replace by V. And all the rest just follows the structure. And so you can prove formally the statement about Motzkin tree. So if you have a definition of is closed is being open with a 0 degree, so no freedom at all. And you can prove the following proposition, which is the translation in code of the statement here, which says for all MT a Motzkin tree, then there exists a T, which is a labeled Motzkin tree, and the skeleton of T is empty and T is closed is the same as saying that MT is closable. You can do exactly the same with uniquely closable lambda terms. So this is again the proposition 2 I just showed, and the proposition 4 is exactly the same, except you have a unique existence here. So these both lemmas, they can be proved formally using the code proof assistant. Now I will talk a bit about the framework to prove isomorphism. So here I recall you what are the what was our first example, which is the correspondence between closable and reclosable, and we'll see that if you look carefully, you will have noticed that with uniquely closable, we are doing exactly the same kind of stuff. And here I try to show how we can do it in a generic way. So reclosable can be replaced by recp for some arbitrary type P, which is here now. And then you have a type T, which is the carrier for your record. So it will be Motzkin tree in the case of closable, but it can be anything else. And you have a property is P, which here is closable. And then once you have all these elements, these 4 elements, you need some operation to go from T to P. And this operation, they have these 2 ones. So from P to T, you just forget what you know about the dependency to go from P to T. So you return to Motzkin tree, you forget that they are actually closable. And the other way around, if you have something in T, which could be a Motzkin tree, for instance, and you have this P, and then you can build the P. And if you manage to have these two functions and you have the, two following property, which is that if you take a V and you transform it, it's of type P, and you transform it to T, you have to make sure it still verifies the P property. And the other way around is that you need to make sure that P to T of T to P of T is equal to T. And once you have all these properties, so these properties, they can be shown automatically in some circumstances in Coq. You can have a generic interface with a module type, which summarizes all these elements, and you can have two instances, for instance, of your, so T can be is P and P can be instantiated either with closable or uniquely closable lambda terms. And the transformation are given here. And all the basic properties, they can be proven automatically using the tactic system of Coq, which means we have a generic way of proving the statements. And then some statements, they can be automatically derived using the functor, which takes the T, is P, P, and all this stuff. And these are the reg P to P, so the proof transformation. And there's just one of the direction, which and the cancellation lemmas, so the round trip lemmas here. You have one direction. If you go from P to reg P, then you can prove automatically in the functor, and the other way around, you cannot, because to do the proof from reg P to P, then the element you receive is an element of P, and you need to know the shape of the inductive data type. So you cannot have some abstract reasoning on P because you don't know anything about P when you're in the module type. So once you know the implementation, then you can do reasoning by induction. So when you know the implementation, you can do it automatically using LTAC, but you can't do it in a generic way because the proof actually depends on the structure of P. Whereas the other proofs, all which are written automatically derived in the functor, they are completely generic and may only rely on these properties here, and they can be derived automatically in any cases. We can do the same for random generators. So yeah, there are three interfaces for random generators, which are parameterized by our family module. So you can build a GenP filter is you want to filter from P. So you can use GenT, and if you have something that can check in an executable way whether an element of T verifies is P. Then you can derive the GenP right from GenP and using the transformation when you go from P to P right, so which means you have the representation in an inductive way and you want to go to the record, and you can do it the other way around as well. So you can use whichever representation is the most convenient for you, because the system can automatically generate the corresponding random generator in the other representation. So there is a small example of the code we wrote to do this generation. I will draw some conclusion and present some perspectives. So about the achievement, what we achieved is we managed to formally describe in the Coq proof assistant some parts of the paper of Bodini and Tarot presented in Lobster 2017. We managed to partially automate the proof of the round-trip lemmas, which connects the various representation of closable or uniquely closable Motzkin trees. And we have some verified random generators as well available. About the perspectives, we want to extend this work with, for instance, typeable Motzkin trees, which is dealt with by Bodini and Tarot in their article, and that we do not handle yet. linear lambda term could be another interesting example to check whether our framework scales properly. We are very interested in looking at what Pierre Lescan presented before, so Catalan, Motzkin, and Schroeder trees. And something interesting would be to revisit the work of Catherine Dubois and Alain Giorgetti about the permutations and rooted maps, and see how the tools we presented here for closable Motzkin trees could be reused. There is a paper available on arXiv that you can look at, and I thank you for your attention. And if you have any questions, I'll be happy to answer.
Thank you. Other questions? Pierre?
Did you consider the formalization of made by Phil Wadler in Agda of lambda calculus? Do you know this work?
No, I don't know, but I look at it.
It's interesting, and also because with a colleague in Novi Sad in Serbia, we developed over this framework, and essentially it's if we think about lambda calculus, you think about the dynamic, the beta reduction. So it should be interesting to have a result on beta reduction, and starting from this kind of formalization. And this is so on the side of Agda, this is what we have done, and with my colleague in Serbia, and with Maciek Bendowski, we have also considered some results on calculi of explicit substitution, which is an implementation of beta reduction, and trying to see some combinatoric result on the dynamic.
We only considered lambda terms as object, and we didn't consider any evaluation on them, but that could be interesting to extend.
Yeah, this is a future. Yeah, it's not the first time I ask these questions, that we should consider the dynamic.
Long, but eventually it will happen.
But to go back to the Agda implementation, it's interesting. It's very neat, and also you take advantage of the fact that it's a calculus of a dependent type. So the fact that you have dependent type, you can define a data structure which carries proofs, and where the proof of some property is part of the term.
Yeah, which is usually quite painful in Coq, so it might be more convenient in Agda. Yeah.
And I like also the syntax of Agda, which is closer to you can type term that is using really lambda. You have a syntax which is the syntax that the mathematicians are used to, but that's another aspect.
Yeah.
Are there other questions? Yes, Martin? Yes.
So you mentioned in your conclusion that you had a formal proof of the random generators.
We have some verified random generators. We have some properties. When you do use the combinators of Quick-Check, you get some insurance. Catherine may be a better place to answer this question.
Yes. So here we have two kinds of verifications. What was presented by Nicolas is that we have a generator that produces records, that is to kind of proof that it is closable. Okay, and we have not proved the generator. Yeah. Because you have in the result a certificate that contains the proof that the object produced has the right property. But we can also verify the generator. For example, you could write by hand a generator that by construction produce closable masking trees, for example, and then you prove that the result produced by the generator have the right property. So
Yes.
you can do both.
Yeah, so basically for understanding correctly, you capture in the type the structure that you want to generate, so you prove that you produce only correct objects. But there are other questions that I would be really interested in, like, can you prove anything about the random distribution, for instance?
No.
Because just proving that you produce correct objects is...
Yes, but you cannot produce any proof about the distribution. I tried, but
Yeah.
I didn't succeed in.
Okay, so thanks.
I had a question just about when you mentioned the work on permutations and maps. What did you have in mind in terms of revisiting that? What kind of results?
When working with Alain, we always have at least 3 different definitions for the same thing. And we never know which one we want to use. And it's not flexible in the sense that when you use permutation, you can describe it with using SS reflect, for instance, which has one representation, and you can have another representation with cycles and this kind of stuff. And sometimes you want to. So the idea is to have really to have some generic definition, which is okay, we're talking about permutation. And if it's more convenient to have one representation, we choose this representation. And if it's more convenient to have another one, we switch to the other one. But what we want is we don't want to choose it at the beginning. We don't want to say, okay, permutation, they are defined like that. We say permutation, they can be defined like that, but if at some point in my reasoning, I want to use them using an alternative equivalent definition, I want to be able to switch from one side to another fairly easily. And that's why we built these functor systems to be able to deal with several representations of the same objects and use them whenever we want. Not just being stuck because in the first file of our development, we choose one representation and we're stuck with this representation all the way down. We want to have flexibility, and that's fairly difficult to achieve in Coq. So what we choose is to have modules to do that. But it's just the idea that we want to separate the actual mathematical concept from the actual implementation or computation way of using them.
Okay. Okay. Thank you. Are there any other questions? So thanks again.
Thank you.